Good day to everyone. First, let me introduce myself. My name is Jeremia Allufi with student ID of 136180044. Here I will present an interplanetary mission in construction for Mars Exploration Rover, being the Rover A, which called Spirit. This is done in order to fulfill Task 3 requirement of Astronautics class AE3210. Here is the outline for the presentation. Firstly, I will explain shortly about the Mars Exploration Rover mission, the purpose, the launch site, the rocket used to carry the rover to the outer space, and also the flight sequences. The next one is the interplanetary trajectory reconstruction strategy that I use in this assignment. After that, I will explain about the calculation that is needed to do the reconstruction and also the assumption used in the calculation. And the final one, I will compare the calculation results with the reference data that I've collected. So first, here's the mission overview. So Mars Exploration Rover was a robotic space mission by NASA in order to reveal a history of past water activity on Martian soil. The rover was launched on June 10, 2003 from Cape Canaveral Space Launch Complex, Station 17A to be specific, and it landed on Gusev Crater on January 4, 2004. The launch vehicle used was Delta II model 7925. It is the same vehicle which successfully launches some of the most known Mars missions, such as Mars Global Surveyor, Mars Pathfinder, and Mars Odyssey missions. Here's the breakdown image of Delta II rocket. It has 3 stages and 9 boosters. I have provided the necessary data that will be used in the calculation inside my report. This is the liftoff phase. So basically at liftoff, the first stage and the second stage, as well as the 9 boosters, will ignite to give the rocket enough velocity to go outside the Earth's atmosphere. And after it went through the Earth atmosphere, it will stay in Earth parking orbit on an altitude of 167 kilometers above the Earth's surface. However, before completing even one orbit, the third stage of the rocket will ignite to begin pushing the spacecraft out onto its interplanetary trajectory towards Mars. And this is the illustration of the interplanetary trajectory of the spacecraft going from Earth to Mars. In this picture, it is seen that the spacecraft did a correction maneuver up to 7 times during the cruise and approach phase of the flight in order to adjust the spacecraft flight path, that is. And after it entered Mars' sphere of influence, the spacecraft immediately fell into Mars' atmosphere and started the landing phase. The heat shield will secure the rover from the heat friction of entering the atmosphere, and after the speed is decreased, the spacecraft will deploy its parachute. Okay, continue to the second part of the presentation. I will explain about the reconstruction strategy that I use. So in this mission reconstruction, I use the patch conic method for the interplanetary trajectory from Earth to Mars. In short, there will be a total of 5 orbits in my calculation. First is the Earth parking orbit, which is circular, and the second one is the hyperbolic orbit that will enable us to do orbital change from a circular to an elliptical orbit. And then the third one is the interplanetary trajectory, that is elliptical orbit around the Sun. After that, the spacecraft will enter Mars' sphere of influence and will change its orbit into a hyperbolic orbit. From there, the spacecraft will be given a velocity change in order to transform the orbit from hyperbolic back to a circular parking orbit, which is a Mars parking orbit. Here is the better illustration of patch conic method that I will use in my calculation. Other than that, I will also use a co-tangential trajectory, meaning that there will be no correction maneuver inside my my calculation. Okay, from the reconstruction strategy I've already explained, now I will show you my calculation for the mission reconstruction. First is the assumption I use. In this calculation, I pretty much use a lot of simplification, which all of it is necessary in order to finish the assignment in time, simply because without the assumption, the calculation will be way harder to be done and the data needed to do the calculation will be harder to find either. So this is the orbital parameters needed to conduct the reconstruction. We have the gravitational parameter of Earth, Mars, and the Sun, and also their mean radius. We also have the known orbital radius, that is the Earth parking orbit, elliptical transfer orbit, and also Mars parking orbit. Okay, next, the true anomaly of the spacecraft position in time of arrival is obtained from the trajectory illustration released by NASA. The true anomaly is found to be around 165 degrees angle. Okay, so now we can begin our mission reconstruction. First is to find the velocity of Earth parking orbit using vis-vis integral. The velocity required is equal to 7.8081 km per second relative to Earth. And then after that, we need to escape Earth parking orbit and enters the elliptical transfer orbit. For that, we use a hyperbolic trajectory that is illustrated on the screen. To find the escape velocity required for the spacecraft to enter the transfer orbit, we first need to calculate the Earth's velocity around the Sun. With the known data, the Earth heliocentric orbit is found to be 29.333 km per second relative to the Sun. And after that, the escape velocity can be calculated using this equation. But then, the transfer orbit velocity at its pericenter is still unknown to us. Therefore, we have to calculate it first before we can continue any further. So this is the elliptical transfer orbit illustration with true anomaly theta equals to 165 degrees angle. So the next step is to find the transfer orbit parameters such as eccentricity and the semi-major axis. The orbit eccentricity can be determined by combining the equation radius of both Earth and Mars position. For Earth radius, the data used is when the spacecraft departs from the Earth, and for the Mars radius, is the distance of Mars to the Sun in time of arrival. From there, the eccentricity of the orbit is found to be 0.1894, and by doing back substitution, we can obtain the semi-major axis. The semi-major axis is around 187 million kilometers. So using that parameters, we can now calculate the velocity of the spacecraft on its pericenter. Also by using vis-vis integral, the velocity is found to be 32.2371 km per second relative to the Sun. And therefore, we can now go back to the calculation for escape velocity. From equation shown before, the hyperbolic escape velocity of the spacecraft is calculated to be 2.9040 km per second relative to the Earth. The escape velocity can be written in terms of energy equal to 8.4333 kilometers square per second square. And also from the escape velocity before, we can determine the hyperbolic parameters such as semi-major axis and the eccentricity as shown in the screen. So from those hyperbolic parameters, we calculate the velocity at hyperbolic pericenter to be around 11.4108 km per second. From that result, we can now know the amount of change in velocity needed to transform the spacecraft trajectory from Earth's circular parking orbit to the interplanetary elliptical orbit. The change in velocity is found to be 3.6097 km per second, and the amount of propellant required to achieve such change in velocity is determined using Tsiolkovsky rocket equation. The amount of propellant required is around 2,411 kilograms. Now we move on to the elliptical transfer orbit again, and we are now preparing to enter Mars' sphere of influence. Using Fish-Visa integral, first, the position velocity at Mars in time of arrival is found to be 22.1834 km per second relative to the Sun. Okay, now all that's left on the transfer orbit is to find the time of flight from Earth to Mars. Here we will use Kepler's equation, but first we need to determine the eccentric anomaly and mean motion of the orbit. For the auxiliary circle, the eccentric anomaly is around 161.8775 degrees angle, and the orbit mean motion is 1.42 times 10 to the power of -7 per second. Then, using Kepler's equation, the time of flight is required to be 225.4403 days. After that, the spacecraft enters the sphere of influence of Mars. The spacecraft will change its trajectory to a hyperbolic trajectory as illustrated on the screen. So, using the same procedure as the calculation of Earth's hyperbolic trajectory, the velocity of Mars' heliocentric orbit is found to be 24.8603 km per second relative to the Sun. And after that, the hyperbolic escape velocity is obtained using the same equation, and the result is 2.6769 km per second relative to Mars. And the excess velocity can also be written in terms of energy, that is around 7.165 kilometers square per second square. So from the hyperbolic escape velocity, the hyperbolic orbit parameters is calculated as before, as shown in the screen. So from the hyperbolic orbit parameters we just obtained, we can now calculate the velocity at the hyperbolic barycenters. It is found to be 5.6138 km per second. This will later be used for calculation of velocity change from the transfer orbit to the circular parking orbit on Mars. Here's the velocity of Mars parking orbit, which is circular. The parking orbit is positioned at altitude of 128 km above Mars surface. From all the required data, we can now enter Mars parking orbit. This is done by giving the spacecraft a velocity change of 2.1246 km per second with the thruster pointed in the opposite direction. The required propellant to give such velocity change is found to be 631.2504 kilogram. So now we have come to the final part of the presentation, where we will compare the calculation results and the reference data that I have collected. So first is to compare the trajectory parameters, that is the first and the second velocity change, and also the time of flight. The error of calculation results shown in the screen arise due to simplification used in my calculation. The most affecting assumption might be the two-body approach and the two-dimensional approximation, because in a real case, the spacecraft experienced gravitational effect from multiple planetary objects, which can lead to, for example, a quote-unquote easier escape from Earth's gravitational effect. That is supported with the fact that the first velocity change in reference data is lower than the reconstruction result. And other than that, the two-dimensional approximation will certainly give a different velocity factor Next is to compare the propellant required to conduct the velocity change. Here I show you the deviation instead of error, so it is easier to see the difference of propellant mass between the calculation results and the reference data. The analysis is more or less similar to the trajectory parameters comparison. However, it is important to show that for the second propellant consumption, large deviation number is produced because the spacecraft didn't actually enter Mars parking orbit. In the real case, the spacecraft went straight to the Mars surface without the help of Mars gravitational effect. The amount of propellant provided in reference data wasn't meant for orbiting Mars, rather it was utilized for trajectory correction maneuvers on a cruise and approach phase of the flight, as mentioned earlier. So by that, my presentation is finally over. So thank you for the opportunity given to me to present my mission reconstruction. I hope everything is clear enough. If there are some missing parts, I have provided all the details in my assignment report. So thank you for your attention.